Thank you. So I'm Lukasz Kostrzewa. I'm from Student Space Association from Warsaw University of Technology in Poland. So I would like to start with presenting rover sequencing and visualization program, which is a tool used by NASA, among others, in Mars Exploration Rover mission. And then I'd like to talk about a few principles of designing graphical user interface, which are, in my opinion, especially important when designing software to control robots. And in the end, I'd like to present control software used for operation of rover Sirius, which is an analog rover developed by our association, which takes part in competitions organized by the Mars Society, like University Rover Challenge. Now, a quick overview of Mars Exploration Rover mission. There were two rovers, Spirit and Opportunity. The mission was a great success. They both survived much longer than planned. They provided lots of great scientific data. But what's important from the point of view of the operator and the control system is that there was a daily mission planning cycle. So that each day the data arrived from the rover. The operator can analyze the data from various sensors, images from the rover. Then based on those, 3D visualization of the terrain surrounding rover is generated, which gives operator better understanding of the surrounding. Then he can generate commands for the next day, or Sol, Martian day, and then all those commands are validated, and if everything's correct, they're sent back to the rover. So the rover provides lots of data from various sensors. It's pretty hard to analyze them. There are really lots of them. There are such features of color coding or plots of data time history to facilitate this analysis. But what's important in analyzing the raw data from various sensors is the possibility to detect some anomalous conditions. For example, too high current draw by some motors, which may lead to some failure of it. So that's a very important step, but it might not give the operator a good information about the surrounding or the state. There are a few onboard cameras on the rover. There's panoramic camera, two hazard avoidance cameras, rear and front, and there's also navigation camera. Panoramic and navigation cameras can create spectral images and stereo images, and it works like that we have two cameras which are pretty near to each other. There's a small angle between them, so when they took two photos at the same time, objects on them are in slightly different position, and based on that difference in position, we can compute the distance of that object from the camera. The knowledge of the distances is very important in creating this 3D model of the surrounding of the rover. This is done using hyperdrive, which is one of the modules of rover sequencing and visualization program. It enables to firstly see the model based on the images, but also to generate a height map or the traversability map. In the left picture, you can see a rover Spirit when it got stuck in like sandy terrain and was unable to move further. So after the visualization, when the operator has good situational awareness of what happens around the rover, what's the position of the rover, they can start generating commands for the next day. It can be done in two ways. There is rover sequence editor, which is based on text commands, which are based on XML, which is a markup language, which is both easily readable by humans and machines. This rover sequence editor also allows using macros, which are kind of a templates with some parameterized command sequences. Because there are lots of command sequences that are very repeatable. For example, before each usage of the robotic arm, temperatures on the drivers need to be set to ensure that the measurements of current draw are correct. It's very important in overcurrent protection. So user creating a command sequence can just put this part responsible for setting proper temperatures to the whole sequence. Such macros are often well tested, and there's very little chance of some failure there. The other way of generating commands is using this hyperdrive tool, which is used for visualization. And the operator can select some points in that terrain, and the rover will approach it. It can be also used to operate the robotic arm, like selecting some points in space, and this software computes the positions relative to the rover, and the rover will set the segments of manipulator accordingly. So when the commands are ready, they're validated on a few levels. First is a check of syntax of that command and also the range of some arguments. Then the commands, especially the motion commands, are simulated in hyperdrive. That simulations also include images. When operator wants to take an image, they can simulate it, so he will know how that image will probably look like. In some cases, it's very important to ensure that the camera is set properly. That images also include shadows, which are computed for specific time on Mars. And in some cases, especially when there are more scientific, not navigational images, it's also very important to know how the shadows will look like. Some tasks that are very complex or hazardous are also simulated on an actual rover in testbed and GPL. In the picture, you can see a Spirit rover, and it tries to roll off the lander. That's a simulation taken in testbed. Now I'd like to talk a little about a few principles of designing graphical user interface for robot control. So the first is separation of concerns. And the idea is to separate a whole software system to a few modules, which somehow encapsulate the data and functionality and have well-defined interfaces between them. It greatly facilitates the development, management, and maintenance of such software system. It also makes it much easier to modify. For example, if you need to make some changes in communication subsystem, we might need only to modify the communication module in our whole software without affecting other modules. In RSVP tool, for example, these two modules, hyperdrive and rover sequence editor, were also created in different technologies. Hyperdrive was written in C++ and rover sequence editor in Java. So such modular approach also enables, in some cases, to use different technologies in some modules. Model view controller is also a pretty popular design pattern. Generally, the idea is to store data or some information about the state of the software application in model, which is not concerned about how this data is presented to the user. It generally stores the data and updates it if needed. a view is only responsible to present the data to the user. It can do it like in whatever way it wants. It can be some table, plot, or any other kind of data presentation. And there's also a controller which allows user to create some changes in data, and it also controls the flow of the data between view and model. This model view controller approach was also very heavily used in the design of RSVP tool. Another important aspect is this data separation. The idea is to store as much data as possible in external configuration files. It makes adding modifications much easier. In Rover Sequence Editor, for example, all definitions of the commands are stored in external XML file. So if this tool needs to be used to operate completely different rover, there won't be a need for big changes in the code itself, but only this configuration file needs to be changed heavily. Now I'd like to present the control software for Rover Sirius, and I'll also show how we implemented that principles I've just talked about on our control system. So a quick overview of our rover and system. There are 3 basic requirements for that. It needs to be easily configurable. Rovers on competitions needs to perform various tasks. Here it has a drilling device and collects some samples, soil samples to analyze. But it can also perform some operations on mock-up panels or collect something from the surface using also a robotic arm. So as our rover needs to be easily configurable and adjusted to different tasks, our software also. We don't have much time to train our operator, so it also needs to be user-friendly. Some of us work on Windows, some on Linux, so it's really good if that's cross-platform. We achieved that using C++ as our language of programming. We also use Qt framework for graphics, but it's also very useful in creating software for communication, files management, and so on. And our rover is still operated. We use SFML library to control input from joystick. Our control software consists of a few modules. This is just a general view of the software. Is much more complex, but there is a protocol on the left, which is our custom library used for communication with the rover. We have rover module, which manages the state of the rover. It stores data from various sensors. It also controls all commands sent to the rover. We have graphical user interface module, which is used to present data from sensors. It also creates some interface to, for example, manage cameras. Our rover is teleoperated, so we also have special module to process data from keyboard and input and joystick and translate it to the commands for rover. As you can see, part of the rover module is sensors model. This is part of our model view controller approach. So we have model that stores data from sensors, for example, from IMU, which gives us 2 vectors. One is from accelerometer and one for gyroscope. It allows us to compute the tilt of the rover, but 2 vectors doesn't give operator almost any information. So on the level of controller that controls the flow of the data, we compute the roll and pitch, 2 angles showing how the rover is tilted, and then on a view we represent that using attitude indicator. We also use this data separation concept in 2 ways. Firstly, we use it to process data from sensors. When we want to process it, we need information about sensitivity of them, or as it's in the case of IMU, also information about the axis of the sensors, how are they aligned with the axis of our local coordinate system. All that informations are stored in JSON configuration file. The other usage is to have some information about devices that are connected, for example, our module for drilling or our robotic arm. We have also a configuration JSON file which gives us more information about that devices. As our rover needs to operate in different configurations, we also need our graphical user interface to be modular and easily to modify. We use tabbed widget, tabbed interface, to manage the different widgets which present some various kind of data or create some interfaces. As you can see above, the top picture, there are a few different windows tabbed. It's the same as in web browser. Some of them can be dragged and put on the other screen. We can stack them however we want. We can, as it's here, make one on the top, one on the bottom. But if there's need, we can completely rearrange them. And it's pretty cool because when we need to go to some place with the rover, we can use one setup. If we now want to control our robotic arm, we can very quickly switch to the control panel of the robotic arm. I would like to thank students from our association who have worked for almost 3 years now and developing that rover, and also our faculty of power and aeronautical engineering who gives us space and supports us financially. And also JPL for sharing images of their software. Thank you very much. Yeah, do we have any questions?
Does your interface provide an easy way for the operator to like toggle to a view of like the camera showing where they're going?
So the question was about the camera, right? How our interface allows user to see actually for that we use external program, which is also developed completely by us, and they cooperate together, but it's a separate tool. But yes, we have such solution. Thank you. Yeah, sure. Yeah, please. Excuse me, can you? No. Actually, it's the question was whether we publish our source code. It's developed in our space association, which is part of our university. So actually, like the rights for that belong to our university. So I'm not quite sure how would it be with publishing that. That's the first problem. The second is that we take part in competitions for rovers. So we also don't really want our competitors to know exactly how our software looks like. Thank you.
I just had a question. You mentioned the accelerometers and the gyroscope for the attitude. Is that a complex system or is that pretty easy? I was just wondering why you can't use maybe just accelerometers. I don't know much about it.
You're talking about this tilt analysis, right?
Yeah, the attitude.
Yeah, but the problem with using only accelerometer is that we can have some drive of that data. There's some shaft that we don't have exact position, but it's also a little bit, there are problems with accelerometers, but when we combine data from both accelerometer and gyroscope, this data is much more reliable. Thanks. Okay, so thank you very much.